In transition now, why don't we look at what are the changing climate attributes in the Western Great Lakes area of the USA. And what I'd like to do is frame how we're making the measurements, what the measurements are showing, and what the consequences are showing, but using this regional structure to frame this. So if you'll bear with me, there are three attributes that are statistically changing in the Western Great Lakes region. Temperatures are changing. Water vapor, what we measure by what we commonly call dew point, is changing in this environment. And lastly, moisture is changing in this environment. So we'll deal with those three attributes in the next few slides. The long-term temperature measurements in the Western Great Lakes, here illustrated with the Minnesota State Climate Database, are a compilation of over 200 volunteer weather observers in the state and many communities that have contributed to this record for well over 100 years. Depicted in this graphic is the mean annual statewide temperature taken from all pooled data each year. And what you can see here is the long-term mean value, which is the central horizontal line that carves through the data, here depicted from the late 19th century up to the present time. You can see in the purple dashed line the long-term upward trend that's detected there, and then in the light blue line out here for the most recent 3 decades, you can see that the slope or the steepness, the change of pace in temperature, is slightly upward. In other words, it's accelerated in recent decades. Another measure of this long-term temperature record in Minnesota to pay attention to is depicted here by this population of dots in the data that occur over the last 2 decades that are above the 90th percentile line. And indeed, we have had some of our warmest years in history in the last 2 decades in Minnesota. I might further state this is true for our neighboring states and provinces like Ontario, Manitoba, North and South Dakota, Wisconsin, and Iowa all show this same character in their measurements. The seasonality in the temperature change signal is depicted in this set of graphics, and I simply want to illustrate that for the winter season, both the persistence measured horizontally here with the depictions of temperature above the mean value, and the amplitude measured by some of the individual years in the winter season on this graphic is much more emphatic than it is in the other seasons of the year. The other seasons of the year do show positive temperature change, but not as emphatically, not as consistently as the winter season does. This is another common characteristic to our region of the USA. It's also depicted here in the long-term graphic of minimum temperature values for the winter months, December, January, and February. Here we see that it is steeply upward trend. The upward trend here is about 4.5 degrees Fahrenheit per century. That's, by the way, despite the very memorable, long, snowy winter of 2013-2014. One of the coldest, longest winters in the landscape history here, at least in our measurement record, and yet it did little to deter this long-term upward trend in the average winter minimum temperature. How are those changing? An illustration from our Minnesota State Climate Database serves the purpose here by looking, for example, at the change in average minimum temperature that's occurred out in western Minnesota in the community of Milan out in Chippewa County. And here we see in this that the average January minimum out at Milan was once upon a time described as minus 4.3 degrees. But what we use as the modern normal value there is now positive 3.7 degrees. That's what we describe as normal now in that same environment where we once said normal was minus 4.3. And you can see the level of change in the winter months. Average minimum temperatures depicted here is rather significant in whole degrees. We can also look at that in the context of looking at minimum, maximum, and overall mean values month by month. And here we pick a central Minnesota location, which is Willmar, Minnesota, located in Candy, Ojai, and we look at the change in normal values going from the 1971 to 2000 period and then describing 1981 to 2010. And what we see here across the board is prolific positive change. We see prolific positive change in the average monthly temperature values. We see it more profound in the winter months, which I've already alluded to, but we also see it more profound in the minimum temperatures. Minimum temperatures are actually changing more than maximum temperatures. Having looked at the data, it's important to tie in our observation of the world around us and the consequences of these changes in data. So here I illustrate a list of the consequences of these changes in temperature that have led to warmer winters and warmer minimum values. We see changes in depth and duration. Our soils and lakes are frozen. We see more rapid breakdown of crop residues left in the fields by our area farmers. We see that they're having to put on fall nitrogen later and later in the fall season because the soils are not cooling down like they once did. We see fewer obstructions to the outdoor construction season, and many general contractors have remarked about this. They're no longer as disrupted by the weather in the winter season as they once were. We see biology changes. We see changes in the overwinter survival rates of microorganisms, plant pathogens, and other things related to area biology. Fewer heating degree days, which has been a benefit economically because the heating demands haven't quite been so severe. Changing plant hardiness zones. Minnesota Landscape and Nursery Association now markets a wider range of plant species for landscaping in Minnesota than they once did, because with the changing temperatures, particularly in the winter season, we can now landscape with plants that formerly were only suitable for more southerly latitudes. We see a longer frost-free growing season. We see increased numbers of freeze-thaw cycles, which unfortunately is playing out with more damage to our pavements and roads. We see changes in animal migration, foraging, and hibernation behaviors. And we see longer exposure times to molds and allergens, with the season extended for molds and allergens to many more calendar days, and therefore our public health area having to account for this in terms of their caregiving. So that's just a sampling of a few consequences related to these statistical changes in temperature. The second feature of our regional climate that's changing measurably has to do with water vapor. This graphic shows the episodic nature of 90-degree temperatures in our western Great Lakes region, illustrating the number of 90-degree days each year in, for example, the Twin Cities area. It's a highly episodic variable, but you can see that in recent years it's exhibited a fairly high degree of variability, and yet we've had a lot of episodes of heat waves in the Minnesota summers. In fact, if we go back and we look at the officially declared heat waves by the National Weather Service, we see quite a prolific history in the state of Minnesota going all the way back to the 19th century. But there's a distinct character change in what we call a heat wave. In this list in front of you, you will see quite a few years listed, some very consequential, where we've actually had serious livestock loss, or we've even had people stressed, and in fact even some mortality of people with these historic heat waves. But all of the years highlighted in red are all driven by high water vapor content, high dew point temperature values, rather than high air temperature values. High air temperature values, for example, occurred in 1936 and 1917 and 1894 in some of these earlier heat waves, where our records show us that the air temperatures actually did achieve 110 or 112 in the case of 1936 even 115 degrees on the thermometer. But more recently, we've also had heat waves, but we've had heat waves with the absence of 100-degree temperatures. This is due to the high water vapor content of the atmosphere. The bar graphs illustrated here, both for the Twin Cities area in the upper right and for Voyageurs National Park down here in the lower left up on the Canadian border, we see these episodes of 70-degree dew points. Now, the reason we use 70-degree dew point here for illustration is because, by definition, an air mass with a 70-degree dew point is indeed a tropical air mass. It is an air mass born at lower latitude. The most immediate consequence of having a dew point that high is it makes the outside air temperature feel even worse than it is. So it inflates the values. And in this context, we go back and dissect summers where the National Weather Service has had to issue heat advisories because the combination of dew point and air temperature has pushed the heat index to values of 100 degrees or higher. And here is a list of those summers when the National Weather Service has had to issue those heat advisories because the heat index has been pushed above 100 degrees. I would point out that we in Minnesota that pride ourselves on our climate resilience, if you will, have endured the highest heat index ever measured in North America. July 19th of 2011, the heat index did reach 134 at Moorhead, Minnesota, which was certified by the Records Committee of the National Weather Service as the highest heat index value ever measured in North America. That was, if you're interested, a combination of a 95-degree air temperature with an 88-degree dew point.